Now that we've discussed in sufficiently general terms the features of a soft starter, let's discuss how they're commonly integrated into electrically controlled system. Note this content is intended to be generally applicable to soft starters and does not delve into specifics about a particular soft starter. It is incumbent upon you to research the connections and specifications for your particular soft starter of interest. For the purposes of this lecture, we're going to assume a general purpose soft starter has three pilot level terminals, A1, A2, and IN, a two-terminal, normally open pilot level auxiliary contact from 1.3 to 1.4 for holding circuit purposes, and three two-terminal primary contacts, L1 to T1, L2 to T2, and L3 to T3. Some advanced soft starters may actually include integrated overload elements too. Note the term contact is kind of an anachronism, since these primary connections aren't physical electromechanical contacts that make and break connections, but rather solid-state devices that do or do not allow current flow based upon input conditions. Sometimes you'll see these devices inside the schematic symbol for a soft starter. By the way, there's a clue for the source of the black magic for those knowledgeable of triacs. Sometimes you'll see these devices on all three, just two, or only one of the primary legs, pending construction of the soft starter. Like I said previously, we'll delve into the dark arts of power electronics and semiconductor devices and circuits in much later lectures. First, soft starters, since they're solid-state devices, ordinarily need to be constantly powered up to run. Note this means that although they present notable advantages, a soft starter may constantly consume a small but measurable quantity of power, even when they're not actively being put to use. This also necessitates more wires, and with more wires come more problems. The pilot level ladder logic may indicate this power connection by placing the A1 to A2 terminals such that they ordinarily receive full pilot level voltage. Note the placement of the E-stop and overload contacts. When the E-stop and overload contact are in their normally closed state, the soft starter A1 and A2 terminals receive full pilot voltage and is powered up and ready for use. This is when the ready indicator light remains constantly lit. We'll discuss how placement of the E-stop and overload devices affect the functionality of the system during a ramp down or power off event in a moment. If you're tracking, you should probably already understand what it does. Note A1 and A2 are direct power connections, and IN is ordinarily the conditional input terminal. The IN terminal of the soft starter is the terminal which initiates closure or opening of the soft starter primary contacts, similar to a coil for an electromechanical contactor. When IN is energized by pilot level voltage, the associated primary and auxiliary contacts change states. Again, I'm using inappropriate anachronistic terms like open and close for this solid-state device. I should technically say it allows or disallows conduction, but old habits are hard to break. Regardless, the presence of the pilot level voltage at the IN terminal initiates the soft starter, and the absence of pilot level voltage at the IN terminal keeps it disabled. An operator enables the soft starter by closing the start push button. Note when the soft starter detects the presence of pilot voltage at the input terminal, the auxiliary holding contact closes, and an operator can now release the start push button. The soft starter remains in the enabled state. The soft starter, upon being enabled, initiates the voltage ramp-up event. Voltage at the T primary terminals goes to the predetermined start voltage value, and then seamlessly ramps up to full voltage over the predetermined ramp-up time period. Inrush current and the mechanical stresses to the driven load are thereby reduced in comparison to a full voltage starter. Additionally, in comparison to electromechanical reduced voltage starters, like primary resistors, part winding, and Y-start delta run methods, inrush current doesn't experience a stepwise disjoint when the transition is made from start to run mode because it is smoothly ramped along. After the ramp-up period, the motor now experiences full voltage and runs at the rated speed and current. The system can now do one of two things: either keep the soft starter in the circuit or bypass it using a method similar to the run contactor in the primary resistor method. This implies soft starters can be divided into one of two categories. 1. Those soft starters that initiate the ramp-up event and then stay in the circuit. These soft starters are designed to carry full load primary current. The IC designates these start and run type of soft starters as having the AC53A utilization category. And 2, those soft starters that initiate the ramp-up event and then are bypassed during run mode and allowed to cool down. The IC designates these start-only type of soft starters as having the AC53B utilization category. For the purposes of this lecture, let's assume we're dealing with an AC53A rated soft starter designed to continually carry full load primary current. After we discuss timer relays, expect to revisit soft starters meant to be bypassed, making use of timers in later lectures. An operator wishing to stop the motor can press the stop button and remove pilot voltage from the input terminal. The auxiliary holding contact opens, and the soft starter can do one of two things. First, it can simply de-energize the motor and allow it to free spin to a halt by instantly dropping applied voltage to 0 volts. Or 2, it can initiate a ramp down event depending upon the user adjustable settings. If the ramp down event is selected, the voltage at the T terminals smoothly drops from full voltage to 0 volts over the predetermined ramp down time period. The soft stop, as this ramp down event is often called, basically keeps the motor energized with progressively decreasing voltage for a user adjustable time period after the stop button has been pressed, for the purposes of bringing the applied load to a smooth and controlled halt. Note the placement of the e-stop and overload contact, as currently implemented, do not necessarily serve to de-energize the input terminal, but rather depower the entire soft starter. Recall those soft starters allowing soft stops momentarily keep the motor energized after an operator presses stop. This isn't necessarily what you want to happen in an emergency. The e-stop therefore serves to not only remove the input signal to the soft starter just like a stop, but also entirely depower the whole soft starter. A completely depowered soft starter, even with the soft stop feature enabled, immediately disallows conduction through the primary terminals. Upon pressing the e-stop, the depowered soft starter therefore immediately de-energizes the motor. Similarly, upon sensing an overload condition, the open overload contact would serve to immediately depower the soft starter and immediately de-energize the motor. As I previously mentioned, advanced soft starters may feature integrated overload elements. In summary, a soft starter is a reduced voltage starter that seamlessly ramps up applied voltage from a user adjustable starting voltage over a user adjustable ramp up time. Additionally, soft starters can be used to progressively de-energize a motor for the purposes of a soft stop. A user adjustable ramp down time determines this period. Soft starters are not electromechanical in nature, but rather solid state. Due to this fundamental difference, one of the peculiarities of soft starter is their failure mode. Depending upon construction, solid-state devices can sometimes fail in the conductive state rather than failing open. This means a faulted soft starter can act like a short between the L and T primary terminals and energize the motor even in the absence of an input signal. This is not exactly ideal. For this reason, soft starters may also include a manual or magnetically actuated electromechanical contactor in series with a soft starter expressly for the purposes of de-energizing the motor in the event of a soft starter faulted in the shorted condition. Here's a graph of line current for a regular electromechanical full voltage starter for a lightly loaded motor. The vertical scale is set to 5 amps per division, and the horizontal scale is set to 0.5 seconds per division. Notice the huge current draw, peaking out around 12-ish amps upon being instantaneously and directly connected to full voltage. Additionally, note the motor accelerates briskly and reaches a stable current draw in maybe 1.25 or 1.5 divisions, meaning it took the motor less than a second to accelerate the applied load. This wouldn't be the method of choice for a fragile electrical distribution network or applied loads necessitating controlled acceleration. In contrast, Consider the graph of line current for a soft starter used on the same lightly loaded motor. The vertical and horizontal scale are set to the same respective 5 amps per division and 0.5 seconds per division. Note the motor takes 3.5 to 4-ish divisions, or around 2 seconds, to accelerate the applied load. Additionally, note that current draw peaks out at only 9 amps. The soft starter therefore serves to limit inrush current demand and the mechanical stresses to the applied load. Here's both curves superimposed on one another so you can compare the two methods. The full voltage starter is in blue. It is characterized by a substantial inrush and a brief acceleration period. The soft starter is in yellow. It is characterized by less inrush current and longer acceleration. Alright, this about wraps up our introduction to soft starters. In conclusion, this lecture took a brief look at soft starters. We learned soft starters are solid-state devices used to reduce inrush current and modify acceleration and starting torque characteristics. Soft starters initiate conduction at a user-adjustable starting voltage and seamlessly increase to full voltage over a user-adjustable ramp-up time. Additionally, soft starters can be used to perform soft stops by progressively reducing applied voltage over a user-adjustable ramp-down time period. Advanced soft starters may include additional features. Soft starters present advantages because they are often lighter, smaller, and longer lasting than their electromechanical equivalents. However, must always be powered on and may fault in the shorted condition. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.